Thank you for allowing me to tell you a little bit about a course I've been teaching at Cal Poly San Luis Obispo. This is my first time at SciPy, and I've actually only been working with Python for about 2 years, so kind of ramped up quickly, and I'm excited to be here and collaborate with all of you. Let me give you a brief outline of the talk. Basically, I'll tell you a little bit about the background of scientific computing in the physics department at Cal Poly, and then discuss the course that I developed, and discuss some of the details, such as the learning assessment, how we do our project-based learning, and examples of those projects that the students developed. And then I'll talk a little bit about how we're assessing the learning objectives from the course, and tell you about an open source project that we've put up on GitHub, and we're looking for collaboration and contributions to kind of improve the scientific computing education for physics majors. Okay. So before I tell you about the course, I want to just give you a little bit of context, my background. I come from high-energy particle and nuclear physics, primarily nuclear collisions at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory, and also the Large Hadron Collider at CERN. And I've also been involved in detector development for a project that studies low-energy nuclear fission at Los Alamos National Laboratory. That's the NIFTY experiment, which stands for Neutron-Induced Fission Fragment Tracking Experiment. And I've been a software and computing coordinator in both of the ALICE and NIFTY experiments, and I have a lot of background in dealing with big data. LHC data sets are petabyte scale data sets, and working with that in large collaborative software development environments over several years. My programming experience in graduate school, I had to learn Fortran to be able to do my dissertation, a little bit of Java, and then transitioned into C and C++, and of course a lot of shell scripting to support that. And most of the software that I work with in my collaborations is written in C and C++. We also have to deal with post-GRE SQL databases. We've done version control ever since I've been involved, starting with a package called CVS. We transitioned to Subversion, and now we're actually transitioning into using Git even in my research collaborations. So my motivation for trying to get students better prepared for working with software tools is that the research I do is very software intensive, and I need them to be able to get up to speed quickly enough so they can help and participate in my research. So motivation. So I'm sure I don't have to convince all of you that we want to try and get more people able to program. I pulled an example from a Wall Street Journal editorial last May and presented it to my students to try and motivate them for why they need to learn to program. But especially physicists, because as many of us know, there are sort of 3 pillars of ways of doing physics, or ways of learning about the universe. Theory and experiment are sort of the traditional ones, and computation is now also one of the main pillars of being able to do physics. And we need to prepare our students better at using those tools. So my philosophy is learn some language, any language, because a lot of the skills are transferable. The basics are universal. And actually, as soon as you learn one language, it's usually easier to learn another. At least that's been my experience. And of course, I'm a very strong advocate of open source tools for many reasons, but I think the students like the fact that it's free. So I come from Cal Poly San Luis Obispo. I've been there for 7 years. Before that, I was a staff scientist at Lawrence Livermore National Laboratory. We're part of the CSU system, and our motto is learn by doing, and the university is very much dedicated to active learning and making sure that students are really doing things developing their own tools and designs and codes and so forth. And part of that is we have a senior project requirement, which is where students actually have to engage in a research project with faculty. Our student population is mostly undergraduates, about 19,000, and we are slated to grow by about 25% over the next 10 years, I think they want to do. In our physics department, we have about 150 majors and 30 tenured and tenure-track faculty. And the reason we have such a good student-to-faculty ratio in physics is because Cal Poly has a very large engineering program, and all of them need to take introductory physics. And since we don't have graduate programs at Cal Poly, we're predominantly undergraduate, there aren't grad students to TA classes for us, so they need a lot of instructors. And we also have a strong commitment to small class sizes. So the typical introductory physics class at Cal Poly has at most 48 students in it, and compare that to most large public universities, that's actually very small. Our department has been recognized as a leader in undergraduate education for physics majors over the past 10 years. We've been involved in a study called Spin Up, which stands for Strategic Programs for Innovation in Undergraduate Physics, sponsored by the APS and AAPT. Let me give you a little bit of background on the scientific computing that is being done in the department at Cal Poly, or has been. We've had a course on the books called Physics on the Computer since 1996, so it predates my time there. And typically students take it in the spring of their sophomore year, and it's meant to be an introductory course in computing. They've had their introductory physics and math courses, but no advanced courses yet. And traditionally, the course has been taught using Excel and Maple and MATLAB. And so when I came into Cal Poly, I found that the students with that training and background were not prepared well to work with me in my research. And so I wanted to try and help develop their skills a little bit more broadly so that they would be more applicable to the kinds of physics that I do, and not just me, but other faculty members that were hired around the same time as me. Numerical and computational methods are not part of our integrated upper division theory curriculum. It's done purely at the discretion of the instructor, and so there's a wide variety of whether there's any computation done in those courses. I personally feel it's important and do it when I teach them, but we also have traditionalists who are very much chalkboard lecture based and don't want to have computation and numerical methods intrude on their theory, lecture theory time. But we have had a multi-year program or effort in our department trying to improve our computational training for our students. And I would say since I got there, I've been heavily involved in that. So what have I done? Well, the first thing I did was actually decide I wanted to learn Python because I didn't know that language yet. And so in 2012, in the spring, I invited any students interested in learning it with me to take an independent study course, and we did it together. So we spent 5 weeks learning Python using Think Python by Alan Downey, and then 5 weeks I put them together in small groups to work on projects. And we picked 2 projects. One was an experimental project related to what I do, which is 3D particle tracking. And one was a theoretical project, which is simulating one-dimensional traffic flows using a cellular automaton model. And as part of this, the students had to do a final project demonstration at the end as a group to show what they had learned. And it was effective at giving the students some basic computational programming training, but it was a 1-unit elective course, so the amount you got out from the students was obviously proportional to what they were able to put into it. So it was a good experience, I think, for them, good experience for me, but I was looking for a way to make it more solid. So as part of our multi-year effort, I'm not going to expect you to read all of these, but as a department, we tried to develop some program learning outcomes for our physics majors. Once they leave us with a degree in physics, what should they know about computation? And so we set down 5 key areas and some sub-bullets in there for the skills they needed. So in programming, numerical methods, symbolic analysis, data, how to interact with data, either collecting it remotely, locally, or through an instrument, and then also instrument control and data acquisition. When it was my turn to teach our Physics on the Computer course last spring in 2013, I took a subset of these learning objectives, because not all of them were applicable to this one course, and put them into the course. And the one thing I added, which wasn't on the list you saw before, was version control. So teaching the students how to keep a good record and archive of their code for reproducibility, and so that they could use it later. The course itself, the way I organized it, I drew a lot of tools from a lot of different places, so you see a lot of logos here representing some of the things, but the fundamental core was using the IPython notebook and GitHub for the students, Git and GitHub, for them to keep their code. And so right now, I'll tell you a little bit about how the course was structured and then discuss some of the projects. So our schedule, we had 10 weeks because we're on the quarter system, and final exam we used for project demonstrations. And I've tried to put together a schedule and identify where each of the learning objectives for the course were being met by the different materials that we were working with. The first several weeks were essentially they needed to learn how to program, because many of the students were coming from zero, no programming background whatsoever. And we used Codecademy as the basis. They did that outside of class on their own time. They worked through the Codecademy Python track in order to learn the syntax and the basics of Python programming. And in class, we had 2 two-hour meetings per week, and for the first several weeks, it was very much instructor-led. I showed them how to use the Unix shell, the command line, version control, discussing why we would do that and how to use it, and then introducing the tools we were going to use for the rest of the quarter, the IPython notebook, and a few other things, SciPy, NumPy, and so forth. And then we basically did what I call tours of many topics in numerical methods and computational physics. So obviously things like interpolation and differentiation in week 6. We went through random number generation, Monte Carlo methods in week 8, and so forth. In week 5, I had a midterm exam just to test that they had built some of their skills. Very simple exercises that they should be able to do in 2 hours, and they basically were. So things like graphing and simple data I/O and flow control and things like that. Also in week 5, I introduced the set of projects and then assigned them to the students. I had 3 projects this quarter that they didn't actually get to choose. I sort of randomly assigned them, and I wanted to make sure we had a roughly even number of each project, so there was a limited number of each, but they were allowed to trade and swap until they got the project they wanted. And then they spent the next 5 weeks working on the tours and exercises on the topics you see here, but then also on their projects. Okay. I want to take a moment just to mention a little bit about grading logistics, because for a course like this for undergraduates, you have to come up with a way of assessing them. And with so many materials in the course, it was, I would say it was one of the bigger challenges in putting together a course like this. So we have about 40 students in 2 sections of roughly 20 each at a time. Each of them did Project Euler problems, which is basically just simple programming exercises to kind of get them to practice their skills. 12 assignments on the different tours and topics that we covered, 1 midterm, and their project, which was 30% of the grade. So all of that added up equals a lot of grading for the instructor. I did have a grader who had taken the course last year who did all of the project Euler grading for me, so that simplified things. And I looked into sort of how much time I wanted to invest in automated assessment, having them submit code that I could test against a script. And at least for this delivery of the course, it was too much effort for me to put together, and so that's something that I'm considering for future. And I put together a set of academic honesty guidelines for the students so that they would understand what the boundaries for collaboration with each other were. And essentially those boil down to you should collaborate, discuss, thank you, and work together, but in the end, no sharing of source code. Everything that you turn in should be your own work. The projects that we did in 2012, 2013, and 2014 are listed here, and the evolution of how we did those projects. So in 2012, I had them do the projects as groups with project demos at the end. In 2013, I tweaked things a little bit. They did the projects individually, and I didn't have demonstrations at the end, and I found that the students were less invested in their work, and I would say the projects were of lesser quality in that year compared to the one before. So for 2014, I had them do individual projects with some group interaction on the design, and then they had to do demonstrations. And I'm going to tell you a little bit about some of the projects now. So the first one, as I mentioned before, was related to my work in particle and nuclear physics, trying to identify trajectories of particles in a sparse data set. And one of the challenges to it was that the voxels, or the elements of charge that they were trying to connect as trajectories, were arrayed in a hexagonal geometry. Now I had them simplify it to a rectilinear geometry for the project, but the goal was basically to try and identify the three different trajectories from the data points that you see there. And this was just an example of one student's project, and he was successfully able to develop an algorithm that could find and distinguish these three trajectories coming from a common point. And this is a simple histogram he did of trying to identify the frequency of orphan voxels that were not attached to any particular trajectory. So there was, he basically developed the algorithm, then studied its ability to do the job it needed to do, and we looked for ways to improve it for subsequent use. Another model that I had the students do in 2013 is something called the Monte Carlo Glauber model. A Glauber model is just basically named after the inventor of it, Roy Glauber, for trying to describe the geometry of a nuclear collision. If you have two nuclei that are colliding, you don't necessarily have them colliding head-on, they may collide peripherally. How can you assess whether that happened or not? And there are methods to do that. And so one of my students developed this as part of his project in 2013, and then put it up on GitHub and did a senior project. And this just shows you using the interactive widgets in IPython that were recently, recently rolled out. You could actually set up an interactive that allows you to play with the type of nuclei that you collide and the impact parameter within which they collide, and see how the different number of particles that are interacting in the collision vary. And so this is some real data that the student produced. The next thing for project for this year was the Schelling Model, which is based on a model of racial segregation that was developed by Thomas Schelling in 1971. And I took the description of the project from a nifty assignment. Stanford has an archive of what they call nifty computer science projects for students. And Frank McCown is the one who posted this one, and so I borrowed it. And had the students use IPython blocks to create an interactive widget to study it. So what you see here is basically a grid of red and blue agents, and you can model their affinity for each other, or you can set a parameter, the tolerance, for how well they want to be next to each other. And the black are just empty spaces. And what the student did was set this up, allow you to change the parameters, and then hit start, and it would actually, I'm not showing you this interactively, but it would go through and move the agents so that they could group together based on their tolerance threshold. And then the students were able to do some analysis of the thermodynamic properties of this. There's an analog to the specific heat, and so this was a graph that some students produced from that project. One of the other projects that I had the students do is estimating Avogadro's number from Brownian motion. So again, this was from a nifty assignment I found at the Stanford archive. Basically doing some particle tracking between the frames of a video. The test data that they had available was some polystyrene bead data that was taken as part of this nifty assignment. And then second part of that, I actually had them go to the biology lab with a video microscope and collect some data on milk fat globules that were suspended in water, and try to analyze that data. And some of the, you can't really see the milk fat in these pictures because the contrast is so different. And so that was part of the project, is they had to figure out how to adapt their code for different types of images. And then they were able to estimate Avogadro's number from basically statistical analysis of that motion. This is my favorite project, the Galaxy Mergers project, which is basically solving the restricted n-body problem. If you have two galaxy cores of very large masses passing each other, and one of the galaxies has a set of particles, massless point particles orbiting around it, when the disrupting galaxy passes by, it will disrupt the trajectories of those particles, and you can model that by basically solve the differential equations. And so this is the YouTube videos that one of the students who did this project posted, and we'll run those. You actually can watch from the disruptors view, that's on the left, and the galaxy view, the main galaxy view as the disruptor comes in. And you can see that the resulting dynamics of the sort of interaction of these two galaxies, and this was all generated by the student. And so it was a lot of fun to teach this class and have the students come up with these results. We did project demos, 5 to 7 minutes oral presentations at the end, and it was peer evaluated, and I was really impressed by the work of the students. And I think that the demonstrations really gave them a strong sense of ownership of the work they did, and was an important part of the learning process that I would definitely repeat, having them do the demos. I'm almost done. Basically, the last part of this, I just want to tell you a little bit about the pre and post assessment. I used a pre-learner survey that I got from Greg Wilson at Software Carpentry to try and assess how well the students were prepared for the course, and then used some of those questions at the end to try and assess how well they had, what their gains were. And the first question was about what programming languages they knew before they started, and they were very, very few. And afterwards, most of them said that they could sort of write this program in Python with very little help. You can see they went from 3 out of 42 saying they could do this to 31 out of 34. So could you write a program to read some data from scratch and calculate the mean and standard deviation? Pretty simple task, but students went from really not knowing how to do this to being able to. A couple other pre and post assessment questions. So this was if you have a file that contains data about the date and the highest temperature on that day, could you write a program to produce a graph of that data? And most of the students beforehand said, no, I couldn't do that, or maybe if I had some documentation, and by the end they were mostly able to do that. I'll skip a couple of these. This one I can summarize quickly as none of them had any experience with version control before, and now they all do. So that's a positive gain. And I asked the students how well they thought that the course met the learning objectives as they were laid out in the syllabus, and I got very positive feedback from them that it met most of the objectives completely or mostly. There were a few listed here that I would probably try to spend a little bit more time on next time. And just to kind of wrap up here, some loose ends and open questions about presenting a course like this. I'm still sort of on the fence about group projects versus individual projects. I think GitHub was a great way to do turning in their assignments and also version control for them. But there are issues around academic honesty with students being tempted to look at other people's code and not do their own work. For undergraduates, where you're trying to train them in these skills, these are important things you have to think about. Yeah, so there's questions about how to separate class time versus homework time. I would definitely try to do more pair programming. We did a little bit of that this year, but more of that next time. And how to divide topics between this, which is an introductory class, and a more advanced class. Finally, I just want to mention that the materials for the course are all completely available online at GitHub. We created an organization called Computing for Physics, and there's student content, so all of the tours and exercises that we did, the project descriptions, and then there are also instructor resources for anyone who would teach a course like this and wouldn't want to start from zero. You can actually download and get all of that information. And we're looking for collaborators and contributions, so anyone who's out there who's interested in working with us, we hope you will contact us. And I'll just summarize by saying I think Python and the IPython notebook are really effective tools for teaching computation to physics majors, and the project-based learning was a very important aspect of the course and getting students excited and engaged, and we're looking forward to future presentations of the course with our students and developing the materials even more. Thank you.